The question that we are going to answer today: why do exact algorithms fail on complex problems? So, if we start with the basics, first of all, we have to see what do we mean by an exact algorithm. So, an exact algorithm is the one that guarantees finding the best possible solution, guarantees finding the best possible solution. That is the global optimum every single time. No compromises. Think of sorting a list. Example, sorting a list. There are different sorting algorithms. If you talk about merge sort, it always gives you a perfectly sorted array. It always gives you a perfectly sorted array. Or if you talk about finding the shortest path, we have Dijkstra algorithm. It always gives you the actual shortest path, not a guesswork. So it is not a guesswork. So these algorithms, Dijkstra, merge sort, all these algorithms, they work very beautifully. They are correct, they are deterministic, they are provable. So there is no problem. The algorithms are correct, provable, deterministic. However, they come with a cost. So there is a cost that is associated with all this, that is time complexity. And for certain types of problems, that cost becomes exponentially large as the problem gets bigger. So some problems, for some problems, the cost is exponentially large as the problem gets bigger. So, to understand why, we need to talk about the concept of P versus NP problem. Okay, it is just enough to appreciate the problem, not just the full theory. So, if you talk about the class P problems, these are the problems that can be solved very quickly. To quickly, what we mean is polynomial time. O of n square or O of n cube, etc. So, the problems such as sorting, okay, shortest path, matrix multiplication, all these things, they all come under this one. There is another class of problem, that is the NP problem. The problems where you can verify a solution quickly. So we can verify a solution quickly, but finding that solution might take exponential time. Okay. So if you talk about TSP's knapsack problem, task scheduling, that is very important for our edge computing, fog computing problems. Okay, the scheduling problems. So task scheduling. So we can verify that yes, this solution is working well. However, to find that solution, it might take lots of time, exponential time. So the key insight that we have to remember is that verification after we get something, some solution is easy. However, discovery is very hard. For example, suppose if I hand you a schedule of 50 tasks and 10 servers, you can check in seconds whether it's good. But finding that good schedule from scratch, that is a very hard part. Okay, so once again, the verification is easy. Once you get the certain solution, verifying that it is working better than other, that is fine. But the discovery of that schedule or that procedure, that is very hard. And that is where these exact methods, they suffer. So if I tell you how fast this can really get out of control, we call it as combinatorial explosion. Suppose you have n tasks, okay, and you have to try all the possible orderings. In this case, it is n factorial ways in which it can be done. So this is a very high number. Okay, if we take suppose 10 factorial, so uh, it's a very high number. Okay, similarly, if n is equal to 50, 50 factorial, furthermore, right? So it really gets out of control. So if our computer evaluates a billion solutions per second, so solving n equal to 50 would take longer than the age of the universe. Okay, because it is multiple times over. And we are not even talking about the multi-objective case where suppose we are trying to optimize for different parameters, for example, energy. So here again, like we have to have the server and the task arrangement, but then we have the energy uh, objective. Then we might have the cost efficiency. Okay, then latency. Like there are different more. objectives. In this case, it can really get out of control. Okay. So actually, the exact methods that we have, these have also evolved beyond the pure brute force. Okay. So the exact methods that we are, in this case, we are kind of vilifying because of their shortcomings, they have also come beyond their brute force uh, methods, and we have different exact methods which are much more flexible. They provide much more options of solving such combinatorial problems. For example, we have the branch and bound, okay, dynamic programming, uh, integer linear programming, etc. So they prune certainly search space. Prune means like uh, if it the algorithm knows that going this way is no use, it might completely cut off this part. Then we can just focus on this part. Okay, so basically they are trying to optimize. Then how we can we should not waste our time and resources in solving something which is actually not going to give us any uh, benefit. However, this pruning strategy, it also hits a wall. So there is some problem, especially when the problem is NP hard. When the problem is NP hard. So in worst case, you're still exploring exponential combinations. You're like you have just delayed the inevitable. Okay, so it's a completely waste of resources. So if you take the examples, we have certain examples like if you talk about the TSPs, so salesmen have to visit N cities exactly once and return home. So what is the shortest route? So if the city's number is suppose 10, so there are many routes to this thing, right? So um, how to solve all these things? Okay, so we have certain solutions for this apart from having the exact methods which can be used for logistic routing, DNA sequencing, etc. Then I talked about task scheduling. Suppose in edge computing, fog computing, IoT, cloud arrangement. In these cases also, we have we have schedules to offload tasks, right? Scheduling, offloading, all these things, and these are all having multi-objective. These are multi-objective in nature, combinatorial problems. So all this is NP hard. Okay. So every new task or node, it multiplies the search space. So it keeps on becoming very big. So exact methods, they simply cannot scale. So this scaling is a problem for exact methods. For their finances and all, they also use all these things. So if the exact algorithms are too slow, what do we do? So we accept a trade-off. We accept a trade-off, like certain kind of compromise. So instead of guaranteeing the absolute best solution, what we do, we have a good enough solution, good enough in reasonable time. Very important, in reasonable time. So this is the philosophy behind the heuristics, heuristic search and everything. So the problem specific rules of thumb, that we find a decent solution and fast, quickly. That is important. Then we have the meta heuristics. So if we add meta heuristics, these are the general purpose frameworks that can be applied across many different problem types. Problem types. So meta means beyond. Meta means beyond. So the meta heuristic algorithms, they go beyond the simple heuristics. They're higher level strategies that guide the search process itself. And often it is inspired by the natural phenomena. Think about the nature, how the nature is solving the hard problems. So ants, they find the food efficiently without any central planner. no central planet. Birds, they flock without any collision. Whales, they hunt in coordinated spirals. Then we have human behaviors also. So these are all emergent, distributed, and good enough solutions to complex optimization problems. So the nature doesn't guarantee the absolute global optimum, but it guarantees survival. Very important quote, I would say. Nature does not guarantee absolute best solution. However, it guarantees survival. And survival, if you see, is often good enough. So meta heuristics, they borrow this philosophy and they explore the search space very intelligently, balancing between the exploration, how much to look for, and exploitation. Like if you have found something, how you can optimize it further. So this balance is very important and it varies across different meta heuristic solutions. And all this is done without exhausting the possibilities that are there. So when we talk about optimization, there is something that is known as no free lunch theorem. It says that no algorithm is best for all problems. So depending on the specific use case, the algorithm need to be varied. Okay, so in this is why we have dozens of meta heuristics and each is having its own strength, its own inspiration, something you will see from aquatic life, birds, humans, ants, insect, reptiles, whatever. Its own way of navigating the search space. Navigation criterias are also different. Some shine on the continuous functions, others on combinatorial problems. Some are great for escaping, the great optima, local optima. Okay, so others they converge faster. So all these algorithms they are having certain differences in their approach of solving the problem. But the inner motivation is this only that we have to find a good enough solution quickly. And this is good for if you look at a networking problem where we need connectivity. So we cannot just wait for the perfect bandwidth or something. In this case, we can use such optimization algorithms. Apart from that, I have another video that I have posted at how you can classify between different meta heuristic algorithms based on 6 factors that I've identified. I've uh, given one video. You can check in my profile. So whenever you are picking up certain algorithm, you can go through these 6 different parameters and you can see whether first of all it is a novel work, and second, even if you are proposing something or modifying something, what expectations can you have when you are looking from this angle of 6 parameters. So I hope this is clear for today. So further we'll discuss in the next topic that what makes the optimization problem sometimes very difficult. These things we'll discuss further. Thank you.